Hello and welcome to Maths with El Profelo. In this video we'll be doing some elementary number theory, and in particular looking at the order of an integer and primitive roots. Okay, so let's start with our definition. Alright, so let's say that we have a is an integer, m is a positive integer, and a and m are relatively prime. Their greatest common divisor is 1. Then, the order of a modulo m, denoted by this notation, ord subscript m with an a, so we'd read it ord of a modulo m, right, is the least positive integer n for which a to the nth power is equivalent to 1 mod m. So let's look at an example to understand this definition. Example 1. Determine the order of 2 modulo 7. Right? So in other words, we want to find the order of 2 modulo 7. By definition, the order of 2 modulo 7 is the least positive integer n for which 2 to the nth power is equivalent to 1 mod 7. Right? By inspection, right, we know that 2 to the first power is not 1 mod 7. Right? 2 to the first power would be equivalent to 2 mod 7. Right? And we know that 2 to the second power is not equivalent to 1 mod 7. We know that it is equivalent to 4 mod 7, right? And what about 2 to the third power? 2 to the third power is equivalent to 1 mod 7 because it is equivalent to 8 mod 7, which has a remainder of 1 on division by 7, or we can say 8 is 1 more than 7. Okay? So, because this power of 3 is the least positive integer n for which 2 to the n is equivalent to 1 mod 7, then we say that the order of 2 modulo 7 is 3. Okay? Now, for the next step, let's look at how we can have an easier time finding this value of n, right? Because if I'm going to have modulo a larger value here, then it could take some time. Like let's say this was modulo 100. Am I really going to go through 100 or rather 99 different possible values of n? Well, here's how we can work through that, and that is proposition 5.1. Right? So proposition 5.1, once again, we're going to say that a is an integer, m is a positive integer, and a and m are relatively prime. Their greatest common divisor is 1. Okay? Then a to the nth power is equivalent to 1 mod m for some positive integer n if and only if the order of a modulo m divides n. In particular, right, and here's our important piece of information. In particular, the order of a modulo m necessarily divides phi of m, where phi is the Euler-Phi function or the Euler-Totient function. Okay, so let's look at an example involving proposition 5.1. Okay, so here we go. Example 2. Determine the order of 2 modulo 13. So in other words, find the order of 2 modulo 13 where we can work with this notation, right? Must be familiar and comfortable with that notation. So, by definition, order of 2 modulo 13 is the least positive integer, n, for which 2 to the nth power is equivalent to 1 mod 13. Okay? by this proposition 5.1, we need only consider positive integers n such that n divides phi of 13. Because 13 is prime, phi of 13 is going to be 1 less than 13, which is 12. So, hence, the set of possible values is n is 1, 2, 3, 4, 6, or 12. Right? Because these are the divisors of 12. Right? Which are the divisors of phi of 13. Now, given, we know that 2 to the first power is equivalent to 2 mod 13, and 2 to the second power is equivalent to 4 mod 13. We know that 2 to the third power is equivalent to 8 mod 13, and 2 to the fourth power is 16, which is equivalent to 3 mod 13, because 16 leaves a remainder of 3 on division by 13. And 2 to the sixth power, which is 64, is equivalent to 12 mod 13. And that's because we could say that 64 is 12 more than a multiple of 13. Right? So clearly, the first power, the second power, the third power, the fourth power, and the sixth power, none of those first values of possible n's work. So, by proposition 5.1, it has to be that 2 to the 12th power is equivalent to 1 mod 13. And you can double check this. You can double check this on a computer, Wolfram Alpha, or different things. But this is true, that 2 to the 12th power is equivalent to 1 mod 13. So hence, the order of 2 modulo 13 is equal to 12, which is phi of 13. This then gets a special name. All right? This gets a special name when the order of a number modulo 13 equals the phi function value of that number. Right? Oh, excuse me. The order of a number modulo m being equal to the phi function value of that m. Okay? And let's do a definition and finish this out. Right? So definition. If r is an integer and m is a positive integer and r and m are relatively prime, their greatest common divisor is 1, then r is said to be a primitive root modulo m if the order of r modulo m is equal to the phi function value of m. So, by example 2, we can then state that 2 is a primitive root modulo 13. Right? And furthermore, if we come up here, notice that the order of 2 modulo 7 is equal to 3. And we know that the phi function value of 7 is equal to 6. Right? Notice that 3 does divide 6. So, therefore, the order of 2 modulo 7, right, equaling 3 does not equal the phi function value of 7 equaling 6. So what we say is 2 is not a primitive root modulo 7. All right? 2 is not a primitive root modulo 7 because the order of 2 modulo 7 is not equal to the phi function value of 7. But 2 is a primitive root modulo 13 because the order of 2 modulo 13 does equal the phi function value of 13. Okay? So that is an introduction to the order of an integer and primitive roots. As always, if you have questions, please do reach out. This has been Maths with El Profe Lo.